If you've been following the playlist, you probably have noticed that some of these lectures are longer than others, at least as it pertains to the first few lectures. And the reason for this is I want to build a firm foundation of knowledge with you prior to really getting into some of the applied aspects of the statistical field. So this particular lecture that we're going to review is test specificity, histograms, odds ratio, and contingency tables. We're going to cover each of these topics briefly, so if you've been following the playlists, this will come up in later videos. And if you're just passing through and you saw the title and you think that this might be helpful as it pertains to your needs as it relates to a class that you're in or research that you're working on, I just want to let you know before I start going through these slides that the contingency table is a topic which we're going to be primarily focusing on as it pertains to this video lecture. So we'll start with test specificity. Specificity can also be remembered as true negative rate. It's the probability of a negative test result conditioned on the individual truly being negative. So in other words, the probability of a true negative test result. All right, that's important to remember. The probability of a true negative test result. So let's do an example. So here's our example. A person infected with a virus has an 89% chance of a positive diagnosis with a particular test. If the test is applied to a person not infected by the virus, the probability of a positive diagnosis is 7%. Suppose that 4% of a population is infected with this virus. Compute the specificity of this test and interpret the results. Now, it's important, not just in the field of statistics, but really within any field in which you're performing analysis, research, or deduction, to be able to break out which elements of the problem or the equation are applicable to your uses. So in this case, the only number that we're really primarily concerned with is this 7% right here. And why is that? Well, if a test is applied to a person not infected by the virus, the probability of a positive diagnosis is 7%. So this would be a false positive right there. So the test is applied to a person not infected, but they get a positive diagnosis of 7%. That would be a false positive. So the rate of a false positive in this case is 7%. So let's compute the specificity of the test and interpret the results. And remember, test specificity is the probability of a true negative test result. So given an uninfected person, probability of a negative test equals 1 minus the probability of a positive test. So if that were the case, then it would be 1 minus 0.07 because 7% is the false positive rate. So 1 minus 0.07 is 0.93. So therefore, the specificity of the test is 0.93 or 93%, meaning that 93% of people without the virus who are tested will receive a negative result. All right, so that's just a quick look at test specificity. Now, I thought that we should probably also discuss histograms briefly, because in later lectures, I'm going to demonstrate how to create histograms through the utilization of the RCommander package as utilized through RStudio. And there's sometimes confusion about what a histogram represents graphically or how to interpret a histogram correctly. So let's talk about that quickly here. A histogram is a graph that shows the frequency of numerical data using rectangles. The height of a rectangle, the vertical axis, represents the distribution frequency of a variable, that being the amount or how often that variable appears. So over here, we have our observations. All right, so this is our observations of var C. So var C is our variable. Here are our observations for that variable, okay? And what we're looking at here along the x-axis is the observation values. All right, observational values. And what the y-axis is demonstrating is the frequency of the occurrence of each one of those observations within our observational series, which is var C. So confusion sometimes arises where where the cutoff is as it pertains to the x-axes. So in this case, let's just take a look real quick. 800 to 802. 800 to 802. Let's see what is included within this observational series. And it's 800 including 800 to 802 including 802. So 800, 801, 802, 802, 802, 802. Here's another 802. So there's 1, 2, 3, 4, 5 observations of 802, one observation of 801, and one observation of 800. So if we sum this together, these categorical observations, that's 7 observations. So there are 7 occurrences of 800, including the value of 800, to 802, including 802. So 801, 800, and 802, they appear in our series 7 times. So as you can see here, our next bar is 803 to 804. Well, let's see, 1, 2, 3, 4, 5, 6 values are contained within that categorical distribution there. So the category 803, including 803, to 804, including 804, is 6. All right? And that's because 1, 2, 3, 4, 5, 6. So all this is demonstrating, again, is the number of observations, the frequency of observation on the y-axis as it pertains to some range, some categorical range of observational data. And don't get confused. Don't get confused as to where the cutoff for one begins and the other ends. If you get lost, just use this particular slide as your guide. All right, it's always going to begin at the subsequent value. So 800, 801, 802, subsequent value is 803. This ends at 804, subsequent value 805, 806. Next is 807, 808. All right. All right, so odds ratio is another way of discussing occurrence. So an odds ratio is the measure of association between an exposure and an outcome. So in terms of odds ratio, the odds of ABC, so this is typically how these particular explanations as far as odds ratio are concerned are structured. The odds ratio of ABC, the odds ratio of ABC is X times higher for Y as compared to Z. All right, so we have an example here. The odds ratio is 19.87 times higher, and it could be lower depending on the type of problem or what it is we're looking to demonstrate. The odds of snow is 19.878 times higher for Chicago as compared to Miami. So odds ratio is just a way of presenting the comparative frequency of occurrence. Now we're going to get into the bulk of this particular lecture, and that is contingency table. So if you've ever reviewed research or have performed research or been a part of a research consortium in one way or another, you've probably encountered contingency tables. So in statistics, the definition of contingency table is a type of table in a matrix format that displays the multivariate frequency distribution of the variables. So we're going to do an example contingency table to hopefully present and illustrate this terminology. So in this example, we have 291 obese smokers, 165 obese non-smokers, 42 non-obese smokers, and 173 non-obese non-smokers. So if we were to put these into a contingency table, the data presentation matrix, as it were, would resemble that which is below. So here we have binary categoricalization. In this case, there were 291 obese smokers, 165 obese non-smokers, here they are, 42 non-obese smokers, and 173 non-obese non-smokers. So as you can see from the breakdown as to how this matrix is structured, our binary categories are on the variable columns and the rows. So we have a binary breakdown. Smoking, yes, no. Positive, negative. Affirmative or otherwise. And obesity, yes, no. And within this matrix, these are unique observations. And what this means will become evident as we go into our next slide. So each one of the individuals contained within one of these categories is unique. So we have, again, a total of 291 smokers who are also obese. So the question then is, how many individuals do we have who are obese, regardless of whether or not they smoke or otherwise? Well, to find that, we would have to sum across these columns. So 291 smokers who are obese, 165 non-smokers who are obese. We sum across this row, across these columns, and we come to 456 individuals. So 456 individuals were obese, whether they smoked or not. Well, how many individuals were not obese, regardless of smoking status? Well, to get that, we would sum 42 non-obese smokers, 173 non-obese non-smokers. We sum these values and we get to 215. So there were 215 non-obese individuals included within our observations. How many smokers were there? Well, we just sum up the values contained within this column then. So we have 291 obese smokers. We have 42 non-obese smokers, which gives us a total of 333 smokers. And you can see that breakdown of what calculates to the sum right here, 291 plus 42. And how many non-smokers are included in our total observational series? Well, we have 165 obese non-smokers and 173 non-obese non-smokers. If we sum these values, we get to 338 total non-smokers. So, breaking this down for column totals and row totals, 456 individuals were obese, 215 individuals were not obese, 333 individuals were smokers, and 338 individuals were non-smokers. And if we are to sum either the column totals together, 333 plus 338, or the row totals together, which is 456 and 215, we come to the value of 671, meaning there were 671 unique individuals contained within our sample series. All right. So if you're presented with a contingency table and your professor or someone on your research team is trying to um, you know inquire, maybe they want to know if you just understand the concept, asks you how many unique individuals are contained within this contingency table, just add up all of the values contained within each cell that are not totals. So 291 plus 165 plus 42 plus 173 will bring you to 671. 671 unique individuals, unique observations, or unique elements within our series. 671. So now I'm going to close out with probably one of the most confusing aspects of the contingency table, and that is row percentage and column percentage. And to understand this, you have to really understand what we went over in the last slide as it pertains to row totals and column totals. So what is being demonstrated here, and how do we come to these figures? I'm just going to go through a couple of them. You can go over the rest yourself just to make sure you fully grasp the concept. This value here, 63.82%, that is the percentage of obese individuals who are smokers. How do we come to this figure here? The 63.82%. Well, you take 291, which is the obese smokers, because obese, yes, smokers, yes, and you divide that by this row total, which is the total number of obese individuals within the observational series. So 291 divided by 456 gives you 63.82%. And this value over here, this row percentage, this is the percentage of obese individuals who are non-smokers. Obese individuals who are non-smokers. And let's take a look as to why that is. Obese, yes. Smoking, no, is 165. We divide that value by the total number of unique obese individuals. And remember, that number is, that sum is calculated from summing 291 plus 165. But in any event, if we divide 165 by 456, we get 36.18%. And again, that is the percent of obese individuals who are non-smokers. Now let's take a look at these column percentages. So what this column percentage is indicating is this column percentage is 87.39%. That is indicating that 87.39% of smokers are obese. And how do we get to this particular figure here? Well, for that, we have to know the total number of smokers, which is 333, and we divide 291 by 333, and we get that column percentage, 87.39%. This column percentage over here, this is the percentage, 48.82%. That's the percentage of individual non-smokers who are obese. Individual non-smokers who are obese. And that value, that quotient value, is derived by dividing 165 by 338. Now, if you're particularly astute, which I know all of you are, you probably notice that if you add this row percentage here plus this row percentage, it sums to 100%. And if you were to add this column percentage here to this column percentage, it sums to 100%. And the same is true for this column percentage and this column percentage. and this row percentage, and this row percentage. Each sums to 100% when added to its pair. So go ahead and try to derive these values yourself. Double check my math, make sure it's accurate. I certainly triple checked it before putting these slides together. I hope that this is able to assist you with whatever it is that you're endeavoring upon, whether it be for a class, for your research, or just to brush up on some of these concepts and terminology. I appreciate you stopping by. If you were able to gain something from this and made it to the end, please consider liking and subscribing. Best of luck with everything that you're working on. Have a wonderful rest of the evening and take care.